There are 64 people registered. We'll see how many we get. Well, Max has joined us as a panelist. Yeah, good morning, good afternoon, good evening, everybody. It's EMinar Wednesday. Gives me great pleasure to host the two speakers of today, Glenn Wilson and Nigel Clegg, on 3D real-time inversion of ultra-deep resistivity logging while drilling. But before I tell you about them, just to remind you to go on the NTNet EMinar webpage, where you can register for upcoming EMinars and see the video link for past EMinars, and also the presentation if the presenters choose to share it. We've got two non-EM EMinars coming up, one from Simon Jowett on mining for net zero, and Mark Zobat, who's going to talk about the geomechanical issues affecting long-term storage. Next week's EMinar, oh, sorry, in a minute. You are on a Zoom webinar, so you can set your audio settings. You can send a chat message to the panelists. You can raise your hand, or you can send a Q&A. Please send your questions in the Q&A. So yeah, anyway, next week, Adam Schultz on faster, cheaper, lighter, developing new instrumentation to broaden access to MT. I mean, one of the bugbears of MT is just the cost of instrumentation. $50,000 for an MT system means we're just getting too few on the ground. So today we have, as I said, Glenn Wilson and Nigel Clegg of Halliburton, who are going to talk about 3D real-time inversion of ultra-deep resistivity logging while drilling. And this is really exciting, hot topic. I'm really looking forward to this. Two CVs, and you'll have seen those when you registered, and I won't go over them except to say Glenn's a global technical advisor with Halliburton, and Nigel is a product champion of Halliburton's EarthStar ultra-deep resistivity service. So I'll stop my share there, Glenn, and invite you to share your screen. Take it away.
Many thanks, Alan, and many thanks for being able to host us for this EMinar as well. It is pretty exciting to be able to come in and talk about this. Obviously, and introducing my co-speaker here, Nigel Clegg. So we're actually going to be tag teaming this presentation. I'll give the first half, and then Nigel's going to go through the case studies for this solution as well. So a lot of obviously the EMinars are around natural fields or controlled source. So I think we're the first EMinar about downhole or borehole kind of logging solutions with EM. And so we really wanted to kind of focus on something unique here, which was the taking 3D inversion and first of all making it real time, and then obviously deploying this in operations. So we're going to step through a bit of this. So a bit of an introduction to logging while drilling, because we fully appreciate that folks on this call may not necessarily be most familiar with logging while drilling, or LWD as we'll just abbreviate it to. And then within LWD, we're going to speak specifically to the tools used to perform ultra-deep resistivity logging. And then we're going to talk around, well, you collect the data, but then you need to do some sort of inversion. So now we're looking to do progressing from, I'd say, the legacy 1D inversion products up to full 3D. And then, as mentioned, we'll then go across to the case studies. So just first of all, just a few acknowledgements. Obviously, within Halliburton, within the Sperry Drilling organization, for basically there's permission and support of this as a product and a technology, and to our colleagues from computational geoscience, and also to our partners, the operators and their partners, for permission to publish the case studies as well. So a little bit about logging while drilling, just to put in the context for everybody. So logging while drilling is where, obviously, as it sounds like, we're actually performing formation evaluation measurements while we're in the process of drilling a well. And so, this cartoon here is trying to show what would be a a fully laden bottom hole assembly, or BHA. But it really, all these tools are interchangeable, and it depends on the well and the objectives in which we're trying to achieve. But obviously, at the very end, obviously you've got the bit where you drill. But then from behind that, you start having the variety of formation evaluation measurements. You'll have gamma ray measurements where you're using this, or not least for depthing. But obviously, being able to look at lithologies. Obviously, we have directional sensors, because these wells that we drill are not just vertical wells. They're high, they can be deviated to lateral. So obviously, understanding where we are in the world is very important. So we have navigation components there. Resistivity is obviously what we're going to talk of today, but that's one measurement we perform during a logging well drilling operation. Obviously, our primary reason for doing resistivity measurements is to look at fluid saturations and porosities. We're obviously measuring density. We measure density, formation density, and then obviously we're also measuring porosity. We have sonic measurements as well, which we can be looking at for slowness, looking at that for rock mechanics. We can also, there's opportunities to do direct sampling of fluids and the like. There's the magnetic resonance, where we're looking at another method doing basically a sourceless porosity measurement in this regard, and further answer products to do fluid discrimination. And there's other measurements in here which we've not included in this cartoon, for example, ultrasonic imaging and the like. But the idea is that all this data that we measure has to then be collected, processed to some degree downhole, and then telemetered back up to surface. And the most common form of telemetry to be used is what we refer to as mud pulse, which is exactly what it sounds like. We're actually using the mud in the mud column itself as basically the conduit being able to send telemeter data. So we're getting into now. Okay, so that's logging well drilling. So we're making measurements continuously as we're drilling the well. So a little bit about now the resolution of those measurements versus what we may be used to with seismic. So here is an image of basically you're seeing the seismic image with the resolution, which which is normally in the order of 20 odd meters for surface seismic. But obviously we're drilling a well, and this well is inches, basically inches in diameter. And so obviously we're at significantly sub-seismic resolution. And so there's a real importance here to be able to use these logging well drilling measurements to kind of build upon or improve our reservoir and formation understanding at a sub-seismic scale. So this is one of the reasons that we start talking of the ultra deep resistivities and the like, is that or deep to ultra deep, because we're actually able to image away from the wellbore at distances less than what the seismic is giving us in terms of resolution. So another constraint here that goes on is really time. So when we're drilling a well, as shown here, the point is that we need to be basically acquiring data, so measuring it, processing it downhole, pulsing it back to surface, and then doing any surface processing in a matter of minutes. And the reason is this: if we're drilling as shown in this particular box, the blue path is the well path, the green box is an area we're going to pick on. But if we're picking a 500-foot section of well, and we're drilling at a rate of 120 feet an hour, then obviously that's going to take us 5 hours to drill. However, we need to be making decisions quite quickly as to where this well is going to be placed. And because we can't have the well path being it needs to be quite smooth, because ultimately we have to run completions and other tools in this well afterwards. So we're having to make decisions early on. So in this particular example, we would need to be making decisions, for example, in the first 30 minutes as to what we're going to be doing for the next couple of hours. So as you can imagine, this is time is of the essence. And so we're not able to just be collecting data, taking it back to surface, waiting a couple of days, weeks, or the like to be able to do some sort of analysis. We're not going to have any impact on the drilling operation if that's the case. So there's a real big drive here to make sure that all analysis is actually performed in real time. And this is the basis of our geosteering operations that Nigel supports, and we'll speak to more in the case study. So a little bit about how do we measure resistivity. There's a variety of tools to be able to measure resistivity in an LWD in LWD strings. The original solution is basically a series of coaxial antennas, effectively, coils wound around the collar, and what we end up doing is not measuring the absolute field, but we end up looking at relative differences. So, for example, we have two receiver coils, and then for each transmitter coil, shown here in gray, we're then able to go about measuring the amplitude and phase difference between these. And it's and one can show that these amplitude and phase differences are proportional to the resistivity and the formation around it. Obviously, depth of investigation is determined by the spacing and frequencies of those coils. So the challenge, however, when drilling in a geosteering operation is that with a coaxial configuration, you don't have azimuthal sensitivity. So whether or not you're approaching a bed boundary above you or you're approaching a bed boundary below you, the response is the same. And so it is giving information about resistivity, yes, but it's not giving you information to help influence the geosteering operation. Should you steer back down? Should you steer back up? And so this led to about 15 years ago or so, the development of the azimuthal resistivity tools. Here's an example of what we refer to as the azimuthal deep resistivity tool, or ADR. And so what we have done is we've actually introduced the receiver coils are actually now tilted. And so, as you can imagine, now as the tool begins to rotate, we're able to have azimuthal sensitivity. The tool has more sensitivity to one side than it does to the other. And so, yet we're still receiving, but otherwise we're recording the same amplitude phase difference between those receivers. And so the benefit of the ADR is that we're then able to have, this is an example of as we approach a bed boundary, how we go about, allocating what's up and down was shown previously, but we're able to now determine where, on what side, or, kind of is the boundary above us, is the boundary below us. And so this is where we're able to use this to be able to, again, this has been used successfully for years now to be able to influence geosteering operations. Again, the depth of investigation is determined by the spacings of the transmitters and the receivers. So for shorter spacings and high frequencies is commonly used. The depth of investigation can be in the order of tens of feet, for example. However, when we start getting into some of these when we're starting to look at some geosteering operations where we want to look further, we have to go about spacing out the coils and spacing out transmitters and receivers and spacing and changing the frequencies. And so that has been is what we've also progressed as we call ultradeep resistivity. And this is where we begin with a transmitter sub, and by sub we mean it's a dedicated tool length. Whereas previously, what I showed you, the ADR and previous one, the EWR, those tools are all on the same collar, the same drill collar. Here, if we go to ultra deep resistivity, the transmitters are on one collar, and then we end up putting receivers on different collars. So now we can actually space them out with, for example, other logging wall drilling tools, or we can put other spacers in there as well. And so now we have flexibility as to what is the range, what is the distance which we want to be able to image from. And so one of the now obviously in terms of processing, we're recording, we're putting current through one, we're recording voltages on the receivers, we're taking that raw data, we're doing downhole processing to basically calculate impedances, and then we're telemetering those to surface. We're doing additional surface processing. And this is where we do our inversion, and then those answer products are fed into the geosteering operation. So we're going to spend more time actually talking around the inversion side of this, and then how this is used in practice. So obviously, to this community, it shouldn't be a surprise, but we'll just obviously discuss, the progress of inversion dimensionality from 1D all the way up to full 3D. So obviously, in 1D inversions, we're assuming that the layered Earth model, the formation only varies in one direction. And so in these cases, we assume that it varies above and below the wellbore. We have the option of going towards because we're dealing with controlled sources, we have the ability to obviously go to a 2.5D inversion, so 3D source and a 2D geology with infinite strike. And so this can be across this can be along the well trajectory. It can be or it can be otherwise across the well trajectory. But then obviously you've got the full 3D, which gives you maximum maximum ability to have changes in all directions and capture the most geological complexity. So we're just going to talk around this kind of progress, but obviously in the art of the electromagnetic inversion for years, it's obviously always, there's been discussions around progressive. This has been the same thing for airborne electromagnetics. It's been the same thing for even MT, is progressing from 1D all the way to 3D. And so just examples of what the 1D inversion would look like. This is actually a pre-well or pre-drill model showing you the multiple layers which are included in it. So we can calculate all of those responses, what the tool is expected to measure, and then we obviously can go about inverting those. Again, in the context of 1D inversion, there's any number of ways to frame this. Over-parameterized, you can have it deterministic, you can have it stochastic. There are pros and cons. There's an abundance of literature describing these sorts of solutions. This is one example that we, as Halliburton, published back in 2018, kind of just for the ultra-deep resistivity. Again, just kind of showing that you have a much finer resolution in your model, but then of course you're solving this for a less number of layers. But it gives you an idea of the sort of structure that you're trying to recover. And these 1D inversions have actually been validated and so this is actually again from that the same publication with my Mark Wu that presented at the SPWLA back in 2018, and this is a really interesting case study. So we actually had two wells as well. Here's a plan view and here's a side view. And so you see the plan view is they're almost on top of each other, the lateral sections. In plan view, one is significantly, one is above the other by approximately 100 feet. And so as we went about doing these inversions on, for example, well 1 by itself and then well 2 by itself, obviously not sharing models between them in terms of inversion outcomes, we're actually able to recover this same lower boundary between the high resistivity and the low resistivity, between those. So this gave us confidence that actually the system, the tool we've developed, was able to have sensitivity in this case out to over 200 feet from the wellbore, because the two inversions were able to resolve the same feature, at the same true depths. Now, that's in the case of some, this particular case, the geology, as you see here, can be closely approximated to 1D. So in these scenarios, we expect that the 1D inversion would perform quite well. Now, as you go to areas where the geology is a lot more complex, then obviously 1D inversions are, and we'll see some of these in the case studies, they're open to ambiguity. And this is the same, again, as has been observed historically amongst, from magnetotellurics to airborne electromagnetics to various other controlled source methods as well. So this is an example of some 2.5D inversions which have been published. But again, the idea is here that obviously 2.5D, you're dealing with controlled sources. You're assuming that the formation has infinite strike in one direction, and then you're letting the other two dimensions vary. So there are, this is again 2.5D has been published for controlled source methods for the better part of 25 years now. And so this should be well known to this particular community. But obviously, we want to try and progress to the full 3D. So the challenge with obviously doing 3D inversion for multi-source surveys is that we have to solve we have to discretize the model and then solve it multiple times for all the source positions. So what I'm showing here is an example of a finite difference grid. For example, for an Earth model, these red dots represent where there may be sources, for argument's sake. And obviously we would need to solve the set of equations for this grid for every source here. Obviously, normally we're going to for these sorts of grids, we're going to iterative solvers, so you don't gain a lot by from source to source. But yeah, it's that usual challenge, right? The discretization, the fact that we're dealing with very fine cells around the wellbore, and they're going to very coarse cells away from it. It just implies that we're dealing with huge numbers of cells in the model. And so it becomes intractable to expect we can use one grid for both modeling and inversion. So, within the community, this has been identified for quite a while. I mean, going back to example, Kalman Newman did this sort of decoupling for marine controlled source EM, basically 15 years ago. It's also been applied to airborne electromagnetics as well. And that is you're able to take your global mesh, and for a given transmitter position, you define a local mesh. And and then obviously you can superimpose those. And if you got multiple sources, each one of those can have its own local mesh. As shown here, this is still preserving that same classic finite difference type of grid. And so you're having to have that real fine discretization in the proximity of the sources. And of course, that doesn't really scale well as you get further away from the wellbore. So again, the number of cells in the models can be quite high, and the actual inversion somewhat inefficient. So this is where so back a few years ago, so Eldad Haber and Christoph Schwarzbach in their paper in Inverse Problems, they kind of described in detail how to go about using OcTree grids as opposed to those regular finite difference type grids, to be able to do airborne electromagnetic problems. And so the idea being that you're able to discretize finely in the proximity of the source and the receiver where you need that discretization, but the rest of the model can be can be much coarser. But then this is basically then running around the entire global grid. And so what we're able to leverage this concept, particularly for logging well drilling. And this is what we're going to, and this is what really enables us to kind of progress to a real-time type of solution, because we're collapsing the number of unknowns in that model down significantly. So another point here as well is, as we go about doing inversion on LWD, we're really interested. We're continually collecting data. And so during a standard inversion, you may be trying to do inversions with all the data which you've gone about collecting. In logging well drilling, once we've drilled past something and it's kind of beyond the sensitivity of where the drill bit is, there's not a lot of sense in terms of maintaining that data in the inversion. So as a result, we end up doing inversion with basic local data. Or this has again been practiced for drilling or wireline applications, or called a moving window. The idea is that you've got a set of data or a set of data which you continually move along the wellbore. So we end up practicing this, and it limits the amount of data we have to invert for. So in the context of, again, looking at an LWD example, the grid on the left here is what the global grid would be, and the grid on the right is what we would need to be solving for a given transmitter receiver pair. And the point here being is that as we would be progressing the drilling operation, then that grid is able to dynamically change and then map itself back into the global grid. And so, one of the but this is where we come to the point. So often over the last literally 15 plus years. Yeah, we end up with this, it's often this challenge, but first of all, it was 3D inversion is not possible. It takes too much time. Now, we start to rub up against, but real-time 3D inversion is impossible. And so this is really to kind of dismiss that. So if we compare solutions, a 1D model, can have in the order of about 30,000 degrees of freedom as you go about solving it. A 2.5D inversion, given that you're discretizing it in terms of 2 dimensions plus the spatial frequency domain, you can typically end up with over 100,000 variables in 100,000 degrees of freedom in those sorts of problems. With the OcTree mesh and the ability to really to limit the volume of sensitivity, we're able to get this down to the order of 30 to 50,000 cells per model. And this means that we're actually able to solve this in literally seconds, compared to what you'd be doing with standard grids with huge numbers of cells and taking hours to days. Now, obviously, all of these solutions can be parallelized, but often when we're in a drilling operation, we need, so to speak, edge solutions. We're often on a rig where we don't necessarily have good communications or high data rates back to a central center where you can run these on a supercomputer. All of this needs to be done on the edge, on the rig. And so, so basically high-end workstations are really what you need to limit yourself to in terms of being able to deliver this. And we're obviously able to do that with a 3D grid. With the 3D OcTree, sorry. Now, in terms of geological complexity, 1D doesn't quite capture it. 2.5D has limitations because obviously you've got full variability, but only in a single plane. But whereas obviously the 3D grids capture that full complexity. The other issues with 1D and 2.5D is that the anisotropy can be included. However, there are some limitations on what that anisotropy can actually be. Whereas in the 3D OcTree and the standard 3D grids, obviously you have that full ability to capture anisotropy as well. So, so the point I want to make here is real-time 3D inversion isn't just possible; it's actually being done. And we've been doing this for quite a while now. So as shown here, this is I'm just going to give you an example of a model study. So this here is an example of a relatively complex, model where we end up having some, faults and folding. The white line here represents the well path, and you can see that generally the model is, it is complex. It's certainly not one-dimensional, and it's not 2D either. So in terms of this is just going to show you the simulation of data. This is an example. As you see, this is what a logging well drilling operation would kind of be like. You see the landing of the well. We're running through the formation. You're measuring all the various components in phase and quadrature. And now we actually have to go about inverting these. So as we progress, so in terms of inversion, what you're going to see here is the top is the actual true model. How do we compare to reality? The bottom is what we're going to see with that inversion of that local data as the BHA moves through the formation. And then the images on the right here are going to be basically gun barrel views down the well. And so you're able to see the formation azimuth be captured as well. And so as I play this is basically simulating that logging well drilling operation, in that you're able to see around and slightly ahead of the BHA. And so obviously it's shown here, it's not just capturing the formation in the plane of the well trajectory, but also we're actually capturing the azimuths around the wellbore very well. So it was a couple of years ago that we actually introduced this as a product, and it's the Earthstar 3D inversion. It was the time it was and still is the only 3D real-time 3D inversion available for logging well drilling. So in that time, we've actually gone through and done a large number of jobs with this, really proved out the technology. And so I think now it's appropriate for me to hand it across to Nigel so he can actually step through the case studies and talk more around this with you. So
Thank you, Glenn.
Nigel.
I will just take over the screen sharing. Okay, and it's this one. Right, so I'm going to look at a few examples, and this is just 3 of the case studies to show you how you might use this sort of tool. So Glenn's obviously covered that LWD tools are used during the drilling operation, obviously for the recovery of hydrocarbons. But what we're looking at when we do that sort of operation is putting the well path in the best zone possible. And by what we mean by that is quite simply, we want to be in the most productive zone where we can drain the hydrocarbons. Now, there are different things that affect your resistivity. One of them is the formation lithology. So the second one, and linked to the formation lithology, is the fluids that are present. So one of the possible hazards that we can have when we're drilling wells, particularly when we're in mature fields where they've been injecting water, is that water may have moved into our target reservoir. So we may have placed wells in that target reservoir, produced from some of them and injected from others, and then a new well is planned to try and target oil that is yet to actually be removed. But in that potential for drilling that well with injection water in the same reservoir, there is always possibilities that we won't just encounter that hydrocarbon, we might also encounter some of that injection water. And obviously, if we drill through zones or near to zones that have injection water in, if we draw that into the wellbore, then we're producing water and not hydrocarbons, which is not the target of this sort of operation. So we'll look at a very simple example. So I've got a sort of little diagram here in the top corner. Here is a well that has already been drilled into the field, and they've been pumping water into the field to push the hydrocarbon towards their production wells. And then they plan to drill a new production well. See if I can get the pointer here. So they're going to drill a new production well, and it looks like it's going to be in a very good zone of hydrocarbons. Now, if we look at inversions, a lot of the inversions for these Ultradeep tools focused on 1D inversions. And as Glenn showed at the start, essentially all they consider is that any change in our formation or fluid resistivity will only occur above or below the wellbore. So if I place my well in this nice oil zone here, all I will see is a zone above and a zone below the well. Now I might drill this well, pat myself on the back for drilling a perfect well in 100% hydrocarbons, and then walk away. And then when the next team come in to start producing from this field, they can draw the fluids into the well, and they potentially can start producing water. And the big question then would be why? So what we need to treat these situations as not just a problem of what's happening above and below me, but what's happening to the sides of me. Because obviously fluid doesn't just move up and down. It moves from pressure zone to pressure zone. And if we look at this example, this is just a synthetic example to show what that inversion may have shown us. So rather than just looking up and down, if we look at a plan view here, we can see in this synthetic scenario here that in fact, a huge zone of water could have been sitting right next to my well path. So my well that I considered to be the perfect well for exploiting hydrocarbons, within a matter of maybe even days or weeks, starts producing water and becomes economically unviable. So this is the thrust of using this sort of three-dimensional data and three-dimensional inversion. Our Ultradeep tools can see out into the formation a significant way. We can steer to avoid hazards, but also we can potentially control how we produce from a well. So even if I had placed my well here, I could block off this section and prevent that water from being drawn in. And you can see very clearly why we got very excited with the availability of 3D inversion, because we can avoid hazards or identify hazards to the sides of the well and not treat the world as just a layer cake. And this is obviously a simple example. As soon as you go and start looking at rock faces or erosional surfaces or faults or structural things, they're all three-dimensional structures. Only in very simple fields do we see that lovely layer cake situation where all the layers are nicely laid on top of each other. So obviously this is a synthetic example. And you can then look at it in different ways. So you can imagine if we're drilling along and suddenly we see that water to the side, we have the potential to steer away from it. We have the potential to be more sophisticated in how we drain this reservoir. But overall, we have a much, much better understanding of what is happening. We're not just treating the world as an up and down problem. We're thinking about it in 3 dimensions. Now that's all well and good because that's synthetic data. But we got asked to test this theory or this sort of practice by looking at a situation where we had very complex water in a very mature field. So this is an excerpt from a paper published at ADIPEC last year. They had this problem, what they referred to as water slumping. So they knew they had water zones that had infiltrated upper parts of the reservoir. They would drill a new well in the target zone, and then that water would start to get drawn into the well as soon as they started producing, or maybe a couple of months after producing. They didn't understand what was causing it, what the mechanisms were. Now, from a 1D perspective alone, you can actually map this water zone, and we saw very clearly that the water zone started to get much closer to the wellbore. So even by looking at it in 1D, we could understand that something was occurring. Now, interestingly, the main low point or the lowest point of the reservoir coincides with the fault. And I say coincides, but in reality, it is likely that this fault is causing the problem. It is likely that there's better fluid flow along that fault. And if we produce this well, that water would get drawn down really quickly around this faulted zone, causing this water slumping and causing this well to become economic. So very quickly, you can see that we can address this situation, identify where that fluid is, and potentially do something about it. So during the job, our simple solution was, we are going to blank off this section and not produce from it. So you can produce oil from the end of the well and oil from the start of the well. Now, we were very lucky here in that we actually crossed that fault so we could see this inversion on a 1-dimensional inversion. But it's very similar to that synthetic I just showed you. This could have just been to the side of us. And even just to the side, if we'd started producing, we would have pulled it into the well. So a 3D inversion of this would give us a bigger picture of what is happening. And in fact, even when you look at this situation where we know what's happening because there's a fault, if you look at the 3D data, and here's some different cartoons of the same data. So this is a side-on view. This is an oblique view. This is that water slumping down towards the well. If I use filters to remove all of the low resistivity material, I can look at that structure around my fault, and I can actually see that that fault is cutting across the well path at an oblique angle. And it shows me that I can track these features using the 3-dimensional nature of the data, rather than treating it as a problem above and below the wellbore. So if this had only occurred just to one side of me, and my fault had not crossed the well path, I could still have assessed that that is where the danger zone is in terms of the water production. So understanding the world in 3 dimensions means when we place these wells, or even after a well has been finished, when we then try and exploit the wells and draw out the hydrocarbons, that we can do it in a much more sophisticated way. Because as soon as you start pulling water into the reservoir, it becomes very expensive. There are mechanisms for removing water when you pull it to surface, but that costs a lot of money. And in some cases, you end up with situations where the water causes what's called a water lock. And essentially that means that it will stop the hydrocarbons from being pulled into the reservoir, and you no longer have any successful production. So the advent of these tools, they're beneficial in two ways. One, they can see all the way around the wellbore, and in fact, in 3 dimensions in every direction. But secondly, out to a distance that we can do something about. Now, a lot of tools can measure sort of images around the wellbore, but they're very close to the wellbore. Some of them are a matter of inches, some of them are a matter of a few feet, but they're not seeing problems very far away. With these ultra-deep resistivity tools, we can detect things out, and laterally we've tracked these things out to about 120 to 140 feet, depending on the resistivity, and vertically, as Glenn said, over 200 feet. So that's a distance that gives us enough room to potentially do something about it, or understand the reservoir on a big scale, rather than trying to understand the sort of micro changes immediately around our well itself. So the other option we can then look at as well, as I said, lithology is also significant when we're looking at these sorts of wells. And we looked at some examples where we had turbidite sands. Now, I'm not sure how many of you are geologists, so I'll do a very brief overview of turbidites. Essentially, when at the edges of the sort of continents, etc., where we have big slopes, you get a big collapse and all the material gets thrown down the slope and flows as a big long flow. As it flows, the sands separate out from the shallow, sort of the fine clay material. So you end up with a sorting of your all of your mixed sediments to create huge sand bodies. Those huge sand bodies are often very clean, and that allows you to then have a very good reservoir potential. But when we're looking at that sort of environment, if you think about it, if we're on the edge of a continental slope and we're looking at slope collapses, that can happen all around. So you don't just end up with a nice layer cake situation. You end up with channels that then get cut by later erosion events and then get more material deposited on them. So you end up with a very three-dimensional situation. It's not a simple layer cake scenario. And if we look at a standard well, so you can imagine this is a standard well path here. Put my pointer back on. So this is my well drilling along. This is my 1D inversion where I'm only looking at resistivity changes above and below. I'm in my nice target massive sand, and then I suddenly drill out and I exit into shale. At best, maybe I will see a thinning of this unit as I hit the edge, but essentially I've drilled into the overlying or surrounding shale units, which are not productive. So that exit is expensive. Now, it means it's expensive in two ways. One, I'm no longer in a hydrocarbon zone, so I can't produce it. And two, it then opens the question of, do we go looking for the sand? Is it that the sand has migrated to one side or the other, the channel has migrated, or has it truly exited? Has it truly pinched out? And if we could look at this from the top, you can imagine the simple scenario. We have a channel and we have literally drilled out of the side of the channel. And a 1D inversion would not allow me to know that situation. I've just exited out of the side. Here, even if I had exited out of the side, I could see that the sand was still there. Or if I'm really quick and the angles of these features are conducive to drilling, I could actually change my well path during drilling to try and remain within that target zone. Now, this is difficult, and the reason it's difficult because when we're drilling, we can only change our well path by a few degrees every 100 feet. You can't do anything more severe than that, otherwise you can't get your completion string down. So it might be that the angle of this change is too much for me to steer by, but we have techniques such as pulling back and side tracking, which allows us to open another well within the existing well structure that would allow us to target the sand. But if I only looked at it as an up and down problem, I would have no idea where the sand was or even if it was present. In fact, I could start drilling an exploratory well that went off in the other direction. And obviously that would be very, very expensive. So again, when we're looking at this sort of scenario, the first option we took is to do a sort of synthetic result to see if we could do an inversion that would clearly pick those boundaries. So here's that side view, and here's that plan view. And this is my sort of synthetic well where I've exited out the side. And I'll just show you a sort of video of the kind of thing. Pointer. The kind of thing that we'd be looking at. Here's my reservoir. As I'm drilling along, my well path is placed nicely in the middle. And I'm drilling my well, and you can see very quickly this boundary, I'm starting to get closer and closer to this boundary at the side. So if I ignore this and only look above and below, this boundary would come in and eventually surprise me. But because I'm looking at 3D inversion, finally I have a tool that allows me to assess where that boundary has gone. And even in the worst case where I exit, I've exited out of the reservoir because I didn't see it in time or we couldn't steer quickly enough. We know where that reservoir is. We know that there is more reservoir. We know it is very close, and we can plan to intercept it. Now, prior to looking at 3D inversion, at best, we might be able to understand some of that potential for where where the channel has gone from seismic data, but a lot of the structures that we're looking at and a lot of the detail is below the sort of resolution of seismic. We're not able to necessarily see that much detail. The advent of ultra-deep resistivity tools and then 1D inversion allowed us to make that sophisticated change above and below. And now with 3D inversion, it allows us potentially to understand what's happening to the sides. And that's a big difference when you sort of consider how complex a lot of these reservoirs are. There's some really potentially complex reservoirs out there that are very good, but you don't want to be drilling multiple wells to try and actually hit that sand or remain within the sand. The less wells you can do, the cheaper it is. You know, each well that you drill is extremely expensive. So we can look at a real world example, and this is real geology. It's quite an interesting one to look at. You see these big red blobs, those are the main sands. They have really high resistivity, they're the cleanest sands. We have some zones where we've got reworking, and then we've got a layer below, which is in fact water, and some areas above, which are our overlying shales. So our low resistivity shales and water are in blue here, and our resistivity target zones, the best zones are in dark red, and the yellow zones are also good targets. So you can see here, this well was planned and drilled as a one-dimensional well, so we only took into consideration TVD, but we looked at this one with regards to 3 dimensions, because all of these changes, some of these structures are caused by erosion, some of them are caused by later squeezing of the formations, can easily happen to the sides of the wellbore as well as above and below. And interestingly, I'd looked at this well quite a lot, and we understood for definite that the oil water contact was going to be very unusual. It was clear from the other offset wells that have been drilled. But I didn't really until recently think about why is it so unusual. You know, these are good sands. They're quite porous. There is no way my oil water contact should change that much. So beyond what we've talked about, or we'll talk about a lot today, we can now invert for something called anisotropy as well as the resistivity. And that's the variance in resistivity, the vertical resistivity and the horizontal resistivity. And we haven't got that material released yet, but it will be released later this year. There's actually a very thin shale that can be identified by that anisotropy, and that is causing this complex oil water contact. So being able to invert in 3D, we can adequately sort of replicate this geological structure and understand what is happening. But now also by looking further at the anisotropy, we can understand some of the complexities in the fluids that we never understood before. So for today's reference from this paper that Glenn actually led, we've got a section at the end that I'm particularly interested in. And this is because this shows the benefits of using 3D inversion, even if you don't use it to steer. If you look at this one-dimensional inversion, and this is what we had real time, these sands look very patchy. They don't look very good. They certainly don't look continuous. And that can affect how I choose to produce it. The big sands at the start, they're interesting, but these big scours are quite two-dimensional. All of this deposition has come sort of out of the page. So these are big two-dimensional structures. But this flaring that we see here of the 1D inversion here is very typical of when a 1D inversion starts to try to resolve a 3-dimensional geology. So this now says to me very clearly that this geology here is 3-dimensional, and it is not just a sort of up and down problem. And if we focus in on that side, that section here, and do a 3D inversion of that data, we can actually see that that sand is very continuous. There are a couple of isolated zones toward the end, but the majority of this sand section here is a continuous sand that has sort of a couple of different things causing its complexity. Firstly, it's sort of the distal portions of the turbidite deposition. So you're getting the turbidite energy is waning, and we're getting thin or small sand channels being cut through the underlying formations. And you can see that here with these sorts of structures. These are channels that we have drilled across. And then secondly, we're seeing vertical structures or vertical distortion of these sands. And that's because after they were deposited, because they were so fluid still, these sands have been squeezed up and squeezed into different structures that are distorting that depositional structure that we saw, or we would have seen if we'd managed to sort of investigate this prior to the other layers of rock being deposited on top. And it shows the benefit of 3D inversion, because this shows what is happening so much clearer than this very patchy, distorted inversion. And in fact, a lot of the distortion we see in some of the other parts of the well are also caused by the fact that that resistivity varies laterally. 1D inversion makes a really, bold statement that everything is fine to either side of me. It's only changes above and below that I am looking for. When we look at this sort of situation, we can see very quickly in a lot of subsurface environments that that's simply not true. Geology varies in 3 dimensions. This is the same section here. I won't go into tons of detail about this sort of plot at the top, but essentially this is an image log. This allows me to look all the way around the wellbore. It starts basically by taking the top part of the tool, going to the left, the bottom, the right, and back to the top. So it's like you're spreading out a cylinder. But the important thing is, where things are symmetrical, then that means that everything is only changing above and below me. When things are skewed off to one side or another, then that means that I've actually got changes to the sides of the well path. And we can use this image here, and we spent time in Glenn's paper doing this, to use this extra independent measurement. This is just a bulk resistivity measurement. It is a measurement azimuthally, but it's measuring everything within that diameter. And you can use this to actually interrogate the 3D inversion results. And because this was a very sort of early deployment of the technology, we're able to show that a lot of these structures are actually replicated. So this 3D inversion is a good representation of this subsurface geology. And these images are available in multiple depths of investigation. It's very difficult to build up a picture in your head simply, but we can use each of those images to actually then quality control this 3D inversion. And it gave us really high confidence that even when the geology is complex, that the inversion is giving us a good representation. And knowing this is how the sand is distributed allows us to understand the reservoir more and potentially exploit it in a more sophisticated manner. And then here's a big picture of the whole reservoir. So each of these we did a 3-dimensional inversion on. This is those big scale swoops that I showed you at the start, which is caused by erosion. So this is actually a second event. So these were deposited as a single sort of depositional event. And then later other events have caused erosion to create channels. You can probably see a second one is coming through here, and there are more. But it allows us to very quickly build up, by combining that 3D EM data with our seismic data, sort of better understanding of how these sands are positioned and what is causing the sort of complex reservoir morphology that we're looking at. And just to show you an example, this isn't the same well, but this is a very similar one to show you how you can look at the data. This is just that 3-dimensional data. This is actually real-time data that we brought in, because after running those original wells, we developed this technology to be able to run it real-time. So obviously the strength in any data set is being able to investigate it. It's very difficult when I do a presentation like this and we show static images, because you can't really grasp the sort of, the full investigative powers of having a 3-dimensional environment. But you can filter out the sort of low resistivities, you can focus in, you can slice the data in different ways. And during a job, we're able to actually look at this sort of structure. So here we drilled straight across the massive turbidite, and we see a sequence of sands. Each of these dark red blobs is a separate sand unit created by a separate depositional event. But by looking at the data in detail during a job, we're able to actually build up that picture of what is happening and then maybe make better steering decisions. Interestingly, in this well, it was a real-time deployment of the data. We had no intention to steer using this data, but we got really nice images of each of these individual sort of sand units, these dark red zones, and actually found that some of them are isolated from the others. So they actually represent isolated sand packages and not a single massive sand package. And when you look even closer at the data, we're then able to pick very thin shale units that are lining these sands, and that's what's isolating them from each other. So whilst we were drilling across at the same TVD, we went from oil to gas and back to oil, which should be impossible if the sands are connected, but it allowed us to understand, even with a test of the real time, how understanding the three-dimensional structures and being able to resolve clearly the geology, because obviously a 1D inversion here may struggle in terms of the 3D structures. It might show that flaring I discussed before. We can actually understand very quickly what's happening. And again, this was a matter of that section was blanked off. They didn't want to produce gas. We can save a lot of potential time and effort in the production sequence afterwards, after well has been finished. Now, the wells I've looked at here are horizontal wells. They're the sort of reservoir sections. But in a lot of wells, we also conduct what's called landing operations. And this is where you're coming down and your well is angling down to hit the target reservoir. And as you approach it, you flatten off to land at the perfect point in the reservoir, so that then when you drill your horizontal section, like we just showed, that you're in a great position to then sort of stay within that sand and maintain a good position. So this was another paper. This is presented at OTC, I think, which was a well drilled in Brazil. They're intending to land. They expected from the seismic, the reservoir to have quite a lot of variability. So these three lines represent the potential variability in the seismic that they were expected. You know, if the reservoir top was much higher than expected, and we carried on with the normal well plan, we'd have landed too low, and our well would have been in a poor position for the horizontal section. If we'd gone for the bottom case and our well had landed above it, we'd obviously be landing above the reservoir and totally missing it. So we had three different cases. So the idea here was to use a one-dimensional inversion, quite simply, to pick those boundaries as we land, and then optimize where we're going to land out. So we can change our well angle to make sure when we hit our target zone right at the end here, we're in the perfect position. So here's that one-dimensional inversion. You can see as we come down here, the reservoir was a lot more complicated than we expect. We start to see the reservoir, and literally within a matter of meters, 20 or 30 meters, we hit it straight away. And then we're straight out of the side of it, and then we hit it again. So this shows from a one-dimensional perspective that our reservoir morphology is extremely complex. So this made it a very difficult decision as to where to land. And then as we hit this section here, you can see it's all very faded. The resistivity values that we were seeing here were not what we expected in the reservoir. Only when we get to these dark red zones were we seeing results that we expected. And interestingly, we're obviously in a communication situation with the rig. We're talking to the rig. The rig was reporting that whilst we were drilling this section here, we were not seeing any sand in the cuttings that come to surface, which is extremely unexpected, because surely we're actually in the reservoir. It's not as good as this reservoir, but we should be seeing sand, and we were not. Now the clue comes a little bit when you look at these images above, that same type of image that I showed before, that goes from the top to the left, to the bottom, to the right, back to the top. Everything is stacking over to the right. Everything through here tells me that all of the resistivity is to the right-hand side of the wellbore. Where my well is placed, I'm actually still in a low resistivity zone, but my 1D inversion is trying to replicate what is obviously much more complicated resistivity as a one-dimensional problem. Something else is happening. So another little video here. So this is that same situation, but this is all of my data. So the low resistivity in blue, and then this is the section where we land out. If I gradually filter away that low resistivity, you see we hit that main point, and then we drill into what appears to be the main reservoir. But as you start to cycle it round, you can see we're not actually in the reservoir itself. We're pretty much drilling alongside what is a subterranean cliff face. So all of the resistivity, all of the target reservoir is sat to the side of me. So there's no wonder I'm not seeing much sand in my cuttings. I'm not in the reservoir, I'm still in that low resistivity zone. And looking at that one-dimensional inversion, it's really difficult to understand where I am. But as soon as you see this, you can see, oh, well, there it is, it's right next to me. I could have planned my landing operation much more carefully and with much more sophistication if I'd understood this complex reservoir morphology. And to be honest, this is expected. I mean, look at the shape of this surface that we have drilled through. This is obviously a series of depositional and erosion events. That can happen along the well path. It also means it can happen to the sides of the well path. So if we use 3D inversion, rather than just having a sort of session where we're scratching our heads to try and understand why the inversion tells me that I'm in the reservoir, but other data doesn't, I can actually build up a much more sophisticated picture of what's going on. So I'll do the conclusions before we get to questions and things. You need to be able to do these things real time. Now, all of the discussions that we've had here, these wells are drilling constantly. As you're drilling, you've got to make those decisions to change your well path as you drill. We cannot wait. You know, some things you can understand after a well has finished. You can drill a well and then look at the data after it's finished, but you then have no ability to change the position of that well. And even if we're going to make a decision after the well is finished to affect how the completion is run, that completion is run literally a matter of hours or days, a couple of days after your well is finished. You don't have a lot of time. So this is why Glenn's point about having a 3D inversion that you can have real time for the data, and maybe within a matter of a few hours, if you're going to do memory data for the whole well, you need to know what's happening straight away. You can't wait a few weeks later and then sort of say, I told you so. We need to make those decisions as we go. And at the speed that they drill these, it has to be pretty much real time. And by real time, we're talking about a matter of a few minutes after it has been transmitted from subsurface. We need to have that result on a screen in front of the geologists. These tools and the way we use it can be used for landing, steering wells, stopping if we're going to see a hazard, or mapping formations to understand them better. So it gives us something that literally bridges that near wellbore measurement you get with standard tools to the sort of really deep measurements we get with seismic. It nicely fills in that gap to give us the detail that the seismic will never gives us. And it's clearly that the 3D inversion is required where we have geological complexity. It's really important to have a good understanding of what's happening in all directions in those complex wells so that we can make those better decisions. And obviously, you know, we've quite established with this technology now. We have quite a lot of case studies where we have validated these results. So certainly in the initial wells that we did, we were very careful, because an inversion obviously is a model representing that resistivity. We were very careful to make sure that we could prove that those 3D inversion results were true by looking at seismic data. A couple of the examples we had 4D seismic, looking at the near wellbore measurements that we can get, and then also looking at things like the one-dimensional inversion and also things like azimuthal image logs, etc. Building up a picture of all those pieces of information allowed us to show that these results were good. We just put the references in here in case you're interested in further reading. Obviously, a lot of these have been presented over the last couple of years, and more will be presented this year. This year's focus is going to be on the sort of anisotropy and the benefits that the anisotropy gives us beyond just that three-dimensional inversion. So thank you very much.
Well, thank you very much, Nigel. That's and Glenn, absolutely wonderful. It's a technology a lot of people on the call might not be that familiar with, and certainly, you know, students viewing this over the next few years are going to be super informed. So one advantage of having two people giving the talk is that one can answer questions. We've had real-time answering of questions by Glenn, which has been absolutely brilliant. So as the questions roll in, I'm gonna ask one, perhaps a technical one. Is there any utility? Would there be any utility in having a source on the surface to give you the larger scale context?
It may be better if Glenn answers that one, because there are technologies that do use that sort of EM measurement. Glenn, do you want to take it?
Sorry, I was actually looking at the question. Sorry, can you just repeat it, Alan?
A source on surface.
Is there utility in having a source on the surface?
Yeah. So again, I would err, and at this point, I would err on the point of saying no. And the reason I say that is, for oil field applications, we're often, you know, literally several kilometers down, right? So we're at significant depth. We're obviously trying to get subseismic resolution. And to be fair, a lot of the times we're offshore. So when you put all these things together, it's really the best resolution we're going to get is when we have source and receiver downhole. And I think that's pretty much. I mean, for maybe for mining applications where you're up in the top, couple of 100 meters, there may be relevance to that, but because in those cases you're not going to be running an LWD string like this. So, but
my guess would be as well. Yeah, my guess would be as well. You would have to go for lower frequencies to get the energy to penetrate that far. And if you're going for lower frequencies and a bigger distance to the source, then you would be imaging bigger structures rather than smaller ones. So you're almost competing with seismic rather than what we're trying to do here is get sort of optimally about 30 to 40 meters or 100 to 150 feet around the wellbore, because that's really the sort of distances that are good for steering and making well placement decisions. But within that, we really want to see that detail close to us as well, because that can make a big effect. If you get too big and too low frequency, then you start losing that detail, and that sort of information already really comes from seismic in the big picture of the whole reservoir structure.
And I think just to add to that, I mean, I didn't touch on it within the presentation, but obviously, when I mentioned that BHA at the very start and all the sensors we can put in there, there are seismic well drilling solutions as well, where you do have the air gun up on surface, for example, and then you have the SWD tool downhole, so you can basically be doing VSPs, right? So that's it's not necessarily an EM solution, but in that case, you're using it to be able to help depth the seismic, be able to put your horizons on the put your horizons on the right depth. So therefore, again, to the point, it's another complementary measurement you're trying to do to make sure that you're going to be landing where you think you're going to be landing. Okay, you're muted now.
There's been a number of questions. I won't repeat the questions. Glenn answered them all, but I just will repeat what Tyler Matheson said, because amazing technology in that tool string. I'm from Hard Rock, so for me, this is like a caveman looking at a Porsche. So we have an open question from Mikhail Studiedov. Thanks for the wonderful presentation. Do you have any examples showing the quality of measured data match by synthetic curves?
I'll throw that to you, Nigel.
By synthetic curves, not sure. We have used this and then done sort of synthetic modeling of offset data.
Sorry. I think what Mikhail's getting at is observed and predicted data, basically.
Right, exactly.
How well are we fitting the data?
Right.
Okay. Examples?
Yes. Yeah. Okay. Not in what we presented here, but in those papers, yes. So when we do the inversion, the route that we take is you're comparing what has been measured by the tool, those 9 components of the EM field that Glenn showed, and then when you do your inversion, it creates a model, and that model then outputs similar curves, and where the two are then compared, then you know how good your inversion is. So when we accept an inversion, then we already have a very good match between our measured curves from the tool itself and those inverted curves. If they did not match very well, then no, we would not be accepting that inversion, because obviously if they're not matching, then it means the inversion result is invalid. So we have a couple of tools that we use. One is just a direct match of the two curves, but also obviously because they're, well, I say two curves, but it's for each component, for each frequency, for each spacing. So it's 9 times 2 times 2 usually, number of curves, but we have a misfit. You're able to calculate a misfit as to how close the two sets of curves are. And we set a sort of very low misfit floor because you want the data to be a really good match, to know that the model we have has high confidence. So from a sort of statistical view, we can see that misfit and go, yes, that's a good model. We then take it a step further, because the problem is you still have the potential for non-uniqueness. Your curves might match perfectly, but your geology may not. You have to always be suspicious, or I'm always suspicious, as I tell the people I teach. We then use things like those azimuthal images and density images and even shallow measurements like gamma to check those models. You know, if I drill into a sand and it's got good resistivity, does my shallow resistivity tool match my ultra deep resistivity tool? Does the boundary dip in the same way that my density dip does? So we're very careful about applying layers of sort of proof beyond that direct comparison of the data itself. But there is a direct comparison available, and there are some pictures in those papers. I just didn't show any here today.
Yeah, I think the inversion with local data I find fascinating, because I've always thought in MT, for example, when they do continental scale studies, that the you know, the resistivity structure under New York isn't really in the data in Seattle. So, you know, the idea of just looking at inverting a local data, and OcTree is perfect for that.
And also the focus on doing the local data, particularly when you're talking about real time and that moving window that Glenn showed, is to be able to keep up with the drilling. If every time you got a new data point, you inverted the whole well,
right.
You know, we start talking about thousands of points. You know, a well can be 3,000 measurement points. If we try to invert all of those, you would very quickly get slowed down and you would not keep up with the drilling. But because we already know what we've drilled through, we're only really interested in inverting what the tool is sensitive to. So essentially we denote a sort of window slightly in front of the tool and behind the tool and around the tool. And as that moves forward, we take that zone and re-invert that zone, so that you're not trying to sort of re-invert everything and slow your entire system down. Because even with cloud computing and parallelization, that would still slow you enough that your results will gradually get to minutes to half hour to hours, you know, behind, and that's no good. You need to make a steering decision instantly, pretty much.
Yeah, Zhusheng Hao asks actually, you mean the real time, how long do you take for having the images shown?
So when the tool does a firing sequence, because it fires a sequence of frequencies, which takes about 1.5 minutes, those measurements are then sent up to surface, which is quite quick. So they get to surface. You're talking about from when you've done your firing sequence to surface is about a couple of minutes. And then on surface, we run the inversion straight away. So that inversion then takes about, I would say, generally about 3 minutes to run the new inversion for that new point. So you're talking about a matter of sort of from the firing sequence to the point that you've got your inversion result, about 5 minutes, maybe a little bit more, maybe a little bit less. And then you're displaying it instantly. You'll tack it on to the data that you've already got. So your inversion gradually builds up as you drill further and further. So in terms of drilling, the results are pretty much near real time. And that's because that's a necessity. You know, even if you wait 15 minutes, you know, people are not going to stop drilling and wait 15 minutes for you to make a decision. But in that 15 minutes, we could have drilled through a fault, or we could have got to the point where we go so close to the top, you cannot steer away from it.
Sorry, I'm unfamiliar with these. How fast do these drill? How long will you drill in those 5 minutes?
Well, it sort of does depend, but generally a good sort of speed is about 100 foot per hour. Some wells, if you go some of the crazy Canadian wells, they're like 500 feet per hour. But generally we're talking about maybe 100 feet per hour. In some harder rocks, it comes down to like 50. But that's the sort of distance we're talking about. And you can imagine 100 feet is quite a long distance. You've got an hour to look at that. You know, a lot can happen in 100 feet when we're looking at faults and all sorts of things.
In 5 minutes, your drill bit is 8 feet ahead or something, right?
Yeah, something in that region, yeah. So you know, this is why you need to make those decisions quite quickly.
So other questions from the audience? If not, I'd like to, here's one. Shiju Du, thanks for the wonderful talk. Can you explain what type of source you use?
Yes, so these are, I mean, all of these tools operate on inductive sources and receivers. You know, effectively they are coils wound around a mandrel. They're a lot more complex than that, but fundamentally you can think of them as coils wound around a mandrel.
And I guess the source So, but the battery, the energy is in the tool or it's sent down?
There are two ways of doing that for a subsurface tool. You can have batteries in the tool. Some tools use a sort of downhole generator. So the mud that's pumped down through the pipe pushes a sort of internal impeller, and that can create energy as well.
Oh, okay.
But a lot of these rely on batteries to power them. So it's pretty powerful lithium batteries. So you can generally get a good 10 days, maybe a little bit longer drilling, as long as you configure your options carefully. And in most wells, that's long enough to have completed the section before you need to pull the tools out.
Dennis Woods asks, do you know of or can you envisage applications for your science and technology other than hydrocarbon exploration, extraction?
Well, theoretically, you can do the same thing for a geothermal well, as long as there is a resistivity contrast to track. We have looked at some options where they want to place geothermal wells in particular parts of a zone, so one near a top of a zone and one near the bottom. And there is a resistivity contrast, so we can track that contrast and place the well parallel to it. So certainly there are applications anywhere where you have a resistivity that you can follow, that you need to place a wellbore at a set distance from that boundary. If there is no resistivity contrast, then you cannot really do anything with it.
And I'd say as well, I mean, I think that just to add to that, obviously, there would be applications again if you're looking at CCS or CCUS wells, right. Similar sort of thing, being able to place those optimally. But everything we're looking at here in terms of application is something downhole, and obviously we're dealing with tool sizes, which are 4, 6, 8-inch kind of diameter tools nominally, which is significantly larger than anything that you'll ever deal with in mining. Right. So and obviously, so in that regard, it's not just the tools, but you're limited by the rigs and everything else in which you're utilizing as well. So if you think of it, it's going to be really energy-related applications that this is primarily used for.
You could surely scale down to an NQ, and then you don't need as much power because you're in hard rock for mining.
I mean, yes and no. I mean, obviously, building, reducing tool sizes is always a challenge. You're trying to, because obviously it's not just in this regard, coils wound around pipe, but obviously all the electronic systems that operate it is there. We're obviously, and again, bear in mind, we're having to pump fluids through the middle of this thing as well. So it's not that it's a solid cylindrical, that's the tool. It's like, no, you're dealing with really an annular. Your tool is an annular, a tubing annular effectively. So no, going down, I don't think we'll get down that small. So,
Tyler Matheson, who's looking at the Porsche, how exactly is data transferred to the surface? Is it frequency shift key in the drill steel itself?
There's two ways of doing it. One is basically pressure related. You have what's called mud pulse telemetry. You basically create pressure changes in the mud, which is detected at surface. So you basically, it's a bit like Morse code essentially. You sort of dot dot dash dash. Obviously, because you're firing a little valve to do that, your speeds are pretty good for downhole tools. We can get all this data to surface, but there are also some drill strings where they actually have what's called wired pipe, which is just as it sounds. They have a wire that runs down from the surface down to the tools, so you can do direct transmission up that wired pipe. Those systems give you a lot more data, but they're more expensive, and obviously if the wire then in some way in that several thousand feet of drill string stops or has a difficulty or broken in connection, then you lose your data. So mud pulse telemetry is still very commonly used, and the systems are very good for getting quite high amounts of high density data to surface.
Amazing.
All coded so that you make efficiencies in terms of how you code or compress data to send it to surface.
Okay, everyone. Well, I think we should let to go. Thanks very much again, Glenn and Nigel. Absolutely wonderful presentation.
No, and thank you, Alan. Thank you for the invite and opportunity to obviously present here. Much appreciated.
Thank
So
you
the
very much.
talk will be available in the YouTube channel, MTNet YouTube, and on the MTNet EMinar page. And Glenn, if you could send me the recording as a PDF, if you allow that, I'll put that over as well.
Okay.
Okay. Bye, everybody. See you next week for Adam Schultz's talk.
Thanks again.